So we're going to start on section 10.2. I'm going to share my screen. If you're taking notes, have those ready. This will probably feel a little fast. And if you need me to slow down, please tell me. I did that in the wrong order. Ding, 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 ding. All right, so here we go. Section 10.2, comparing two means. All right, so in this section, we will again be describing the shape, center, and spread of the sampling distribution, but this time for the difference of two sample means. We need to check if conditions are met for doing inference about mu1 minus mu2. We should be able to construct and interpret a confidence interval to compare two means. We also will need to be able to perform a significance test to compare two means. And lastly, we need to be able to tell the difference between when we should use a two-sample t procedure or a paired t procedure, which is the paired t procedure is what we saw at the end of section 9.3 yesterday. All right, so we need to be able to tell the situations where we would use either of those or one of those. So that's the goal for today. We'll see some of these things. It's going to be a lot of notes. And again, next week, we'll be seeing examples and doing practice problems with these. All right, so what if we want to compare the mean and some quantitative variable for the individuals in population 1 and 2? Our parameters of interest are the population means mu1 and mu2. The best approach is to take separate random samples from each population and to compare the sample means. Suppose we want to compare the average effectiveness of two treatments in a completely randomized experiment. We use the mean response in the two groups to make the comparison. So again, we have the scenario where we're comparing things within two populations and the situation where we're comparing results in an experiment based on treatments. So we have these two different circumstances in which we can conduct inference about the difference of means. And once again, we have some new notation. Population or treatment 1, we have parameter mu subscript 1, statistic x bar subscript 1, and sample size n subscript 1. Similarly for 2, we have mu sub 2, x bar sub 2, n sub 2. Once again, we can use different things for the subscript as long as we're defining what it is and which thing it goes back to. Does it go back to population 1 or population 2? Again, if population 1 is adults and population 2 is children, we can use subscripts A and C to stand for adult and children to identify our variables. Or you can easily just default to using 1 and 2. You just need to name what they go to. To explore the sampling distribution of the difference between two means, we're going to start with two normally distributed populations having known means and standard deviations. Based on information from the U.S. National Health and Nutrition Examination Survey, the heights in inches of 10-year-old girls follow a normal distribution. And again, this is our notation for a normal distribution, n parentheses 56.4, comma 2.7. The first number listed here is the mean. Second number listed is the standard deviation. The heights in inches of 10-year-old boys follow a normal distribution, n parentheses 55.7, comma 3.8. Suppose we take independent SRSs of 12 girls and 8 boys of this age and measure their heights. Once again, notice the sample sizes are not the same, and that is okay. What can we say about the difference? The difference x bar subscript f minus x bar subscript m in the average heights of the sample of girls and the sample of boys. Right, so in this case, they use subscript f and m for female and male. Okay. So we do some distributions here. They use their Fathom software again. We generated an SRS of 12 girls and a separate SRS of 8 boys and calculated the sample mean heights. The difference in sample mean heights was then calculated and plotted. We repeated that process 1,000 times, and the results are below. Right, so they have the sampling distribution for the sample mean heights for the girls, 10-year-old girls, and again for the 10-year-old boys, and then the difference. All right, and what can we notice about the shape, center, and spread of the sampling distribution of the difference of the two heights? Well, just like the parent populations, it is normal. The mean is the difference between the mean of the girls' heights and the boys' heights. And again, the standard deviation will have a unique calculation that we will look at. Is there anything I can clarify so far? Any questions? So then both x bar sub 1 and x bar sub 2 are random variables. The statistic x bar sub 1 minus x bar sub 2 is the difference of these two random variables. Once again, in chapter 6, we learned that for any two independent random variables, x and y, the mean of x minus y is the mean of x minus the mean of y, and the standard, or not standard, the variance of x minus y is equal to the variance of x plus the variance of y. So that gives us everything we need to be able to come up with the sampling distribution and describe it. Right, if we have an SRS of size n1 from population 1 and mean mu sub 1 and standard deviation sigma sub 1 and an independent SRS of size n sub 2 from population 2 with mean mu sub 2 and standard deviation sigma sub 2. The shape, when the population distributions are normal, the sampling distribution of the difference in the means is approximately normal as well. In other cases, the sampling distribution will be approximately normal if the sample sizes are large enough. Right? N subscript 1 is greater than or equal to 30, or n subscript 2 is greater than or equal to 30. Both must be large enough, right? Not just one. So again, we have these two same conditions, right, for the shape of the sampling distribution that we saw yesterday with the proportions. The mean of the sampling distribution is mu sub 1 minus mu sub 2, and the spread will be the standard deviation of the sampling distribution of the difference in the means of the sample means is the square root of the variance of sample 1 divided by n1 plus the variance of sample 2 divided by n2, as long as each sample is no more than 10% of its population. And I'm sorry, that's the variance of population 1, variance of population 2, not the sample. I apologize. All right, so this, when they ask you to describe the sampling distribution of the difference between two sample means, they want the shape, center, and spread in this way. Does anyone need a moment to write anything down from this slide? And then we have a picture of all of these things right here. The curve is our sampling distribution of the difference of the sample means. The horizontal axis represents all possible values for the difference of the sample means. The middle is the mean of mu1 minus mu2. And the standard deviation helps determine the width of our distribution. And again, that is the square root of the variance of population 1 divided by the sample size of sample size from population 1 plus the variance of population 2 divided by the sample size from population 2. So when data come from two random samples or two groups in a randomized experiment, the statistic x bar sub 1 minus x bar sub 2 is our best guess for the value of mu1 minus mu2. When the 10% condition is met, the standard deviation of the sampling distribution of x bar 1 minus x bar 2 is that same thing we just saw. Right? Sigma of x bar 1 minus x bar 2 is equal to the square root of variance of population 1 divided by n1 plus the variance of population 2 divided by n2. If the normal condition is met, we characterize, or we standardize the observed difference to obtain a t statistic that tells us how far the observed difference is from its mean in standard deviation units. Right, so when we're dealing with means, we will typically use a t statistic rather than a z statistic. And this is because we will typically not know standard deviation or the population mean. We're trying to estimate them. That's addressed here. Since we don't know the values of the parameters sigma 1 and sigma 2, we replace them in the standard deviation formula with the sample standard deviations. The result is the standard error of the statistic x bar 1 minus x bar 2. All right, and we get the following formula. Standard error of x bar 1 minus x bar 2 is equal to the square root of the standard deviation of sample 1, or I'm sorry, the variance of sample 1 divided by n1 plus the variance of sample 2 divided by n2. And then we get our t statistic. T is equal to x bar 1 minus x bar 2, the statistic, minus mu1 minus mu2, our parameter, divided by the standard error, or the standard deviation of the statistic. And that gives us our t statistic. It follows the same pattern as how we calculate the t statistic for one sample, that we saw in the previous chapter. Right, your test statistic, in this case is t, is always going to be equal to your statistic minus your parameter divided by the standard deviation of the statistic. All right, and that's actually what's given to you in your formula sheet. You're not going to be given this formula necessarily, but you'll be given the format. Test statistic equals statistic minus parameter divided by standard deviation of statistic, and it'll give you the different pieces that you can plug into that based on what you're dealing with. Okay. The two sample t statistic has approximately a t distribution. We can use technology to determine degrees of freedom, or we can use a conservative approach using the smaller of n1 minus 1 and n2 minus 1 for the degrees of freedom. All right, so that means if you're using table B with your t distribution, you use the degree of freedom that is the smaller between the two sample sizes. So if one sample, like in our previous example, we saw, I think, sample size of 12 and 9. Right, 12 minus 1 is 11, 9 minus 1 is 8. You would use 8 for your degrees of freedom. That is the smaller of the two. Or you can use technology. And we'll show how to use the calculator to do these calculations and get the t statistic value and the p value and all those things for significance tests and confidence intervals. We can use our calculator to get these, and it will give us what the degree of freedom is, but it'll give us all the other stuff we need to. And we'll see examples of that next week. And depending on what you're doing, you could get kind of different answers between table B and technology. So it's important when you're doing the AP exam that you show or state which one you're using, because the answers will vary. The two sample t statistic. Conditions for performing inference about mu1 minus mu2. These conditions apply to confidence intervals and significance tests. We once again have random 10% and normal large sample. And once again, these things must be checked for both populations/samples. All right, the data come from two independent random samples or from two groups in a randomized experiment. All right, so if you're doing an experiment and maybe the individuals were not randomly selected, however, the treatment was randomly assigned, that's random. We have the random condition covered. We have the 10% condition when sampling without replacement. Check that N1 is less than 10% of the population size it came from, and N2 is less than 10% of the population it came from. And again, this goes when sampling without replacement. So there are circumstances when we're doing experiments when we are not sampling without replacement. That means we do not need to check the 10% condition. And again, we will see examples of this. Then we have our normal large sample, right? So both population distributions or distribution of responses to the two treatments are normal, or both sample sizes are large enough. N1 is greater than or equal to 30 and N2 is greater than or equal to 30. This again is from our central limit theorem. It goes back to chapter 7. Right, that's how we say large enough. Right. If either population treatment distribution has unknown shape and the corresponding sample size is less than 30, we need to graph the sample data from both samples, right, and assess the normality of the population or treatment in the distribution. We do not use two sample t procedures if the graph shows strong skewness or outliers. Slight skewness, that's okay. Something that you can't tell if it's an outlier or not, we're not going to say it's an outlier. If you graph something and it is obvious there's a point that's an outlier, no two sample t procedures. Right. There may be times if you are going to say something is an outlier, you need to be able to back it up. Meaning you need to use like the 1.5 times IQR method, right, to show that something could be considered an outlier. I think that's the only one specifically we've done in this class, if I remember correctly. There's also another formula for using standard deviation, but it only applies, really, it's only supposed to be applied to things that are more normally or symmetrically distributed. So if you have something that's skewed, it's not really accurate. So use the IQR times 1.5 method is going to be a little more consistent for showing an outlier. That was probably a little too much of me rambling. All right, does anyone need a moment to write any of this down for their notes or anything previously? I think I was going kind of fast. So we now have our confidence intervals for mu1 minus mu2. Right, when the conditions are met, our random 10% large normal or large sample, an approximate C% confidence interval for mu sub 1 minus mu sub 2 is the difference of the sample means x bar 1 minus x bar 2 plus or minus t star, our critical value, times the square root of the variance of the first sample divided by n1 plus variance of the second sample divided by n2, where t star is the critical value with C% of its area between negative t star and positive t star for the t distribution with degrees of freedom from either technology or the smaller of n1 minus 1 and n2 minus 1. And recall we find our t star value using table B and the degrees of freedom and the confidence interval that we're looking for. All right, so we're using the degree of freedom column, right? And along the bottom, you have confidence interval percentages. And so you kind of line those things up to get your t star. So we need a moment to write any of this down. So that brings us then to our significance tests. Right? An observed difference between two sample means can reflect an actual difference in the parameters, or it may just be due to chance variation in random sampling or random assignment. Significance tests help us decide which explanation makes more sense. The null hypothesis has the general form H naught such that mu1 minus mu2 equals the hypothesized value. We're often interested in situations in which the hypothesized difference is 0. Then the null hypothesis says that there is no difference between the two parameters. And we get H naught such that mu1 minus mu2 equals 0, or alternatively H naught such that mu1 equals mu2. The alternative hypothesis says what kind of difference we expect. Either that the difference will be greater than 0, the difference could be less than 0, or just that it is not 0. Could be greater than, could be less than. We get a two-sided test in this case. Okay, so it follows the same pattern as the hypotheses that we looked at in chapter 9. It's just now we have two parameters. Would anyone like a moment to write anything down from this page? All right, to do a test, we need to standardize x bar 1 minus x bar 2 to get a 2-sample t statistic. Again, we have test statistic equals statistic minus parameter divided by standard deviation of statistic. And that is the same exact formula we saw earlier. However, keep in mind, typically our hypothesis is that mu1 is equal to mu2, or that their difference is 0, so you'll just be doing minus 0 over here. To find the p-value, use the t-distribution, table B, with degrees of freedom given by technology or by whichever one is smaller, n1 minus 1 or n2 minus 1. And once again, you should be specific on which method you're using. If you're using table B and degrees of freedom that are smaller between the two sample sizes, you need to make a note of that in your work. If you're going to use technology, you need to make a note of that in your work because the answers will be a little bit different depending on the method you use. Would anyone like a moment to write anything down from this page? So then we get our 2-sample t-test for the difference between two means. This is our inference method when doing a significance test. Suppose the conditions are met to test the hypothesis h not such that mu1 equals mu2 equals a hypothesized value. We must compute the t statistic, which is the same thing we've seen previously. T equals the difference between the sample means minus the difference between the parameters, which would be whatever the hypothesized value of those parameters is, divided by the standard error. We find the p-value by calculating the probability of getting a t statistic this large or larger in the direction specified by the alternative hypothesis h sub a. We use the t-distribution of degrees of freedom approximated by technology or the smaller of n1 minus 1 and n2 minus 1. And remember from what we saw in chapter 9, when we use table B, we get a p-value that has a range. Most of the time we won't land exactly on a t-value that's on table B. And so we'll get that, okay, the p-value is between 0.05 and 0.1, or 0.001 and 0.02 or something. Yeah, you know, it depends on the values on the table. Not remembering off the top of my head. So we get a range. When you use technology, when you use your calculator, you will get a specific p-value. All right. Usually, regardless of the method you use, you should come to the same conclusion. When you wrap it all up over your 4-step process and state your conclusion based on the given significance level, right? Alpha equaling 0.01 or 0.05. Both methods will get you the same result if things have been done properly. And again, we need to do these things wisely. In planning a 2-sample study, meaning if you are planning the study yourself, it works better if you can choose equal sample sizes when you can. It doesn't have to be same sample sizes, but things work a little better if they are. Do not use pooled 2-sample t procedures. We will not go into what this is. It's not, we don't need it. However, it does show up as an option on things like in your calculator. It will give you the option when doing a 2-sample t test to do pooled data samples. Don't select it. Choose the other option. There's only two. It says pooled or something else. I don't remember what it says. Just make sure pooled is not highlighted. Right? If it's an option, don't choose it. We're not using it. We are safe using 2-sample t procedures for comparing two means in a randomized experiment. And this is addressing the fact that we don't need to check the 10% condition as long as the treatments were randomized. We do not use two sample t procedures on paired data. In that case, we use the one sample t procedure based on the difference between the pairs of data. And again, we'll see examples of when to use paired versus when to use two sample t procedures. And beware of making inferences in the absence of randomization. The results may not be generalized to the larger population of interest. And this randomization is referring to how you have selected the individuals participating in your study in an experiment. If those individuals were not chosen at random, if they were volunteers, or if they were just the people available to participate, then you can only make an inference about the people like the ones who participated in the study. You cannot make an inference about the larger population of interest. So you have to be careful on how you word your conclusions and your answers. All right. Does anyone need a moment to write anything down from this screen? Then that is the end of the notes for comparing two means. And again, we will see examples of these things next week. I have a lot of problems already selected for us to go through, if you guys practice with, so we'll see all these things. All right, and stop sharing my screen. All right, so then with that, the chapter 10 module almost has like most of its parts done, right? I have the notes and resources for both sections. I have the practice problems and practice problem solutions for section 10.1 now up and running. I am currently finishing up the practice problems and solutions for section 10.2. Those should be done before the end of the day today and posted. So if you have the time and you want to look at those resources or those practice problems, please do so. And other than that, again, remember it's the end of the grading period. Anything that you would like to have included in your grade, make sure that it's been done. The assessments for chapters 6, 7, and 8 will be included. So if they are not done, you will get placeholder grades. The multiple choice assessments will get a placeholder grade of 0 if they are not submitted, and the free response questions get a placeholder grade of 1 if they are not submitted. All right, so please keep that in mind. And again, I use the word placeholder grade because I do not penalize for late work. Once it's turned in, you will get the grade that you earn on those things and nothing less. All right, is there any other questions, comments, or concerns? All right. Well, then I hope you guys have a great weekend and a great rest of your day, and I will see you all next week.